The next thing we're going to look at is simplifying radicals by factoring. So sometimes the number that we have underneath our radical is not going to be a perfect square or a perfect cube or whatever we're looking for. So we're going to want to find factors that will give us what we want, so we'll be able to simplify. So for instance, if we look at the square root of 20, 20 is not a perfect square. So what I'm going to do is go over to the side and I'm going to start writing out the factors of 20. So 1 times 20, of course 1 is a perfect square, but that's not going to help me because I already have 20 underneath. The next one is 2 times 10. Neither one of those is a perfect square, so I'm going to keep going. 20 is not divisible by 3. It is divisible by 4. 4 times 5 is 20. And this time, I do get a number as one of the factors that's a perfect square. So what I'm going to do is rewrite my 20 as 4 times 5, because now we can split that, and then the square root of 4 is asking me for the square root of a perfect square, which we know. So we can write this as 2 times root 5, which is just 2 root 5. You don't have to show this step right here. I'm just trying to be continuous in the way I write things, okay? Now for the next one, the index is a 3. So we're looking for something that is a cube root. Well, 24 is not a perfect cube, so I'm going to do the same process. And again, the first set of factors, 1 is a perfect cube, but that doesn't help me because it doesn't change anything. So I'm going to keep going. 2 times 12. Neither one of those is a perfect cube. The next one would be 3 times 8. And 8 is a perfect cube. So I'm going to rewrite cube root of 24 as the cube root of 8 times 3. Now the order that you write it isn't important. You can write the cube root of 3 times 8 if you wish. I always like to put the thing that's going to simplify in the front. It's just easier for me. And then we can split this up into the cube root of 8 times the cube root of 3. And then we know what the cube root of 8 is. That is a perfect cube, so that's just 2. And it's going to be times the cube root of 3. Alright, and the next one, we have a number on the outside, so we'll deal with that through the problem. But our main purpose first is to find the factors of 45. That is not a perfect square. So if we start listing the factors, again, 1 times 45 isn't helpful. It's not divisible by 2. We get 3 by 15. Neither one of those is a perfect square. It's not divisible by 4. The next one we get is 5 times 9, and 9 is a perfect square. So I'm going to rewrite the square root of 45 as the square root of 9 times 5. And now that 5 being out front, the operation between there is a multiplication. So this is 5 times root 9 times root 5. So we have 5 times. I know the square root of 9 is 3 times root 5. So that's just going to leave me with 15 root 5. Alright, these last two of these that we're going to do, these are a little more difficult than the ones that we just did. They're really the same thing, along with some stuff that we did in the last lecture. If you look at this first, I see square root of 40. So let's just deal with that first. So if we write the factors, of course 1 times 40 isn't helpful. 2 times 20, neither one of those is a perfect square. I think the next one is 4 times 10, and the 4 is a perfect square. So I'm going to rewrite the 40 as 4 times 10. Now the more difficult part comes in with these variable terms. So you remember that we've been writing things. Let me come over to the side for a minute. If we had the square root of 9, we've been trying to write it as the square root of 3 squared so that we can cancel those out. So that's going to be where we're trying to get. So if the index is a 2, the first thing I want to try to do is get my exponents to be even so that they're divisible by 2. So y to the 8th, that one's already an even number, so we're okay. Now the square root again is going to be easier here than the cube root. If we're dealing with an index of 2, so it's a square root, and you have an odd exponent, all you have to do each time is rewrite it as x to the 1, and then x to your odd exponent minus 1. 7 minus 1 is 6. So basically I'm trying to get this to be an even exponent. If it's odd, if you subtract 1, you're going to have an even number. So if I had x to the 11th, I would write it as x to the 1 and x to the 10th. Okay? Now I'm going to leave, the y to the 8th because that one is even. Alright, you don't have to rewrite the square root of 4 as 2 squared if you don't want. But I think it probably is helpful. If you remember, this is the part that we were doing. I want to rewrite that x to the 6th so that I have an exponent of 2, like I showed you in the example over here. So remember before, if I want x to the 6th, I need 2 times what is 6, and that gives me a 3. And then the y to the 8th, we want the same thing. We want a 2 out here. So what I have to multiply times 2 to get 8 is 4. And of course the reason that we wanted to do that is because we're trying to get it to cancel with our index. Okay? So I'm going to write these in descending, well, not descending order. I'm going to write them in the order where all the things that we're going to be able to take out the rooter first. So I have a 4, that's a perfect square. The x to the 3rd to the 2nd power, and the y to the 4th to the 2nd power. All of those are going to be able to come out. And then we have left 10 times x to the 1st. So now we know the square root of 4 is 2. Not the square root of 2, but 2. And then remember, my index and exponents can cancel, so that x to the 3rd, y to the 4th is going to come out. And we're still going to have our 10 x to the 1st underneath. Alright, I know that that is a fairly intimidating problem. It's often one that students don't enjoy. but hopefully we'll get practice with a couple of them and you'll get comfortable. So for the next one, the difference is it's a cube root, and of course, as you've seen from the pattern, cube roots are generally a little bit harder than square roots. But I'm going to start the same way with my number. I want something that has a perfect cube this time. So if we start with 1 times 40, then 2 times 20, neither of those is a perfect cube. The next one would be 4 times 10. Neither of those is a perfect cube. The next one would be 5 times 8. So this is what we want. 5 times 8 will give me 40. So I'm going to rewrite the 40 as 8 times 5. Alright, now this time it's not as simple as just taking an odd exponent and subtracting 1. This time, because we're looking for a cube root, we want our variables to have an exponent that is divisible by 3. So this y to the 9th, we're not going to have to change that one because 9 is divisible by 3. For the x to the 7th is not divisible by 3. So we want to rewrite it as the product that has an exponent that is divisible. So this one's a little harder. We have to think, if I have the number 7, what's the closest thing that is divisible by 3? And the closest thing is 6, right? So if I need 7 and I split it out into 6, we need 1 more. Alright? So we've got 8 times 5. We can't do anything with the x to the first. We're going to rewrite this one. We want a 3 on the outside because we're trying to match the index. So 3 times what is 6 is a 2. Then for the y, we want a 3 on the outside so it matches the index. 3 times what is 9 is 3. So I'm going to write the ones that are going to be able to come out again, and then the ones that are going to be left. So we know the cube root of 8 is 2, so that comes out. Then remember, my index and my exponents can cancel. So it's going to be x squared y cubed. And then what's left underneath is 5x. All right. Thankfully, I think that's about the worst of this. This next thing that we look at, this isn't so bad. Adding and subtracting radical expressions. These work a lot like collecting like terms when we have polynomials. As long as we have radicals that have the same thing underneath, we treat them like like terms. So just the same as, let's look at an example. If we have 2x squared plus 3x squared, then we say it is 2 plus 3x squared is 5x squared, right? It works the same as if I have 2 root x plus 3 root x. Then that's just going to be 2 plus 3 root x is 5 root x. Okay? So it's kind of like collecting like terms. So for the first one, I have like radicals. So all we're going to do is add the numbers that are out front. So 9 and 3 gives me 12 roots of 7. That's it. And doesn't matter if they're cube root, it's the same thing. As long as these are the same, we can do the operation that's out front. So 4 minus 8 is negative 4 cube roots of 2x. Alright? Now the last one involves the stuff that we were just doing with the simplification. What we want to do is try to simplify what's under those roots as much as we can. So the first one, I have a 12 underneath my root. So I'm going to do the same process we've been looking at. Of course, 1 times 12 doesn't help. 2 times 6, neither one of those is a perfect square. And then 3 times 4. So this is the one I want. So I'm going to rewrite my square root of 12 as 4 times 3. Now the 2 square root of 3, the only thing we can get for factors of 3 is 1 and 3. So we're not going to be able to change that one. For the 72, 1 times 72, of course, is not helpful. The next one is 2 times 36, and 36 is a perfect square. So I'm going to rewrite this as 36 times 2. And then this is similar to what we were just doing. I'm going to write this as 6 times root 4 times root 3 minus 2 root 3 plus root 36 times root 2. So this is 6 times, we know the square root of 4 is 2, times root 3 minus 2 root 3 plus the square root of 36, we know is 6, and it's times root 2. So we're just going to clean this up. 6 times 2 is 12 roots of 3 minus 2 roots of 3 plus 6 roots of 2. Now you notice these first two terms, they have the same radical term. So we can combine those two. 12 minus 2 root 3 plus 6 root 2. 12 minus 2 leaves me with 10 roots of 3 plus 6 root 2. And then since the root 3 and root 2 are not like, we are finished.